Good afternoon, everyone. Thanks for joining us. We're going to get started here in a couple minutes. We'll just wait for a few more people to join, and then we'll get going.
Hello, welcome to today's See You on the Weekend webinar, A Mission to Touch the Sun. My name is David Means and I'll be your moderator. I'm the director of the Office for Outreach and Engagement, which sponsors these lectures. CU Boulder is a world-class public research university. We're deeply rooted in Colorado, but the work of our faculty connects our state to the planet as a whole, and as we shall see today, to space beyond. See You on the Weekend is a recurring series of lectures, free and open to all, designed to share some of the most significant and interesting research and creative work taking place across our campus with the general public. We're so glad you could join us today. Just a few logistics before we get started with the presentation. Attendees may submit questions by clicking on the question and answer or Q&A button located at the bottom of your Zoom window. Throughout the lecture, about every 10 to 15 minutes or so, there will be a Q&A break during which the presenter will respond to as many of the questions you have submitted as possible. While we likely won't have time to address every question, we will make a point of getting to those that are most common. If you submit your questions as they come to you throughout the talk, this will give us a chance to review them as we go and see which ones are the most popular. Along with responding to questions submitted through the Q&A function, as we go, the presenter will also occasionally call on audience members who have raised their hand during Q&A breaks using the raise hand button that can also be found at the bottom of your Zoom window. This webinar is being recorded, and by Monday, we will add a link to the recording on our website. Okay, now it's my pleasure to introduce today's speaker. David Malaspina is an assistant professor in the Department of Astrophysical and Planetary Sciences and a professional researcher in the Laboratory of Atmospheric and Space Physics, known as LASP. He received his Bachelor of Science in Physics from Purdue University and a doctoral degree in physics from CU Boulder in 2010. Still early in his career, Professor Malaspina's contributions to our understanding of space physics is significant, with 148 peer-reviewed publications to his name, 28 of these as first author and 120 as a co-author. Professor Malaspina's research is highly experimental and applied. He has worked with award-winning engineering teams on several major space flights, one of which we will hear more about in a moment. He and his team have been responsible for the design, fabrication, testing, calibration, and operation of instruments and signal processing electronics upon which research successes of these missions depend. We're extremely pleased to welcome Professor Malaspina to CU on the Weekend.
Thank you, David. Much appreciated. Am I good to share now? Okay, take that as a yes. All right, I'm assuming everybody can hear me. Let's see, can maybe one of the folks who are panelists let me know if I'm audible?
Yes, you're sounding good.
Beautiful, thank you. Okay, so welcome everybody. Thank you for coming. Today, I hope to share with you a bit about the Solar Probe mission, which has been renamed as the Parker Solar Probe. And the title of this talk is A Mission to Touch the Sun. That's exactly what this spacecraft is designed to do, is get closer to the sun than anything has ever gotten and try to scoop up pieces of the stellar atmosphere as close to the sun as we can reasonably get. So this presentation and everything in it is based on an enormous amount of work by a large number of people at NASA, at APL, and then people associated with the instrument teams who put together, designed and built and tested the instruments and are now operating the instruments on the spacecraft. So what you're looking at here is a picture of the sun, right? That's actually a photograph of the sun taken by a space telescope, and then artistically superimposed is a picture of the spacecraft. This is just a detailed CAD drawing. This is not, a photograph or anything. Okay, so who am I? As I was already introduced, I'm an assistant professor in the Astrophysical and Planetary Sciences Department, and I'm a researcher at LASP over on East Campus. And specifically, I work in the Space Plasma Group at LASP. The Space Plasma Group has been involved in a number of major NASA missions in recent years, some of which you may have heard of, including the Van Allen probes, the MMS mission, Parker Solar Probe, which I will talk about now, and MAVEN. Okay, and I'm going to tell you this story in 4 pieces. Specifically, we're going to start with a history type piece, a little bit about the background of why do we even know that the sun emits a solar wind, and why do we care? And what have we learned about it so far? And then we're going to get into solar wind science. So what specifically do we want to understand, and why do we need a solar probe? Then I'm going to discuss about how we prepared for this mission, both in terms of securing funding, which is sometimes very difficult, mission design, instrument design, which are also very difficult. And then I'll share with you some of the results and discoveries that Solar Probe has made. My intent here is to take about 10 to 15 minutes per section and then have some back and forth with you all. So we'll see how that works out now that we're on Zoom instead of in real life. Okay, so what I'm going to start with, I cheated a little bit. I said I would start with Act 1. Well, here's an Act 0, where I'm going to discuss a bit of terminology. There's a few things to understand before we jump into this. I think that will make the rest of the talk more accessible. The first is I want to describe what a plasma is. So you may have heard this word. You may have heard it related to, for example, blood plasma or plasma TV. When I talk about plasma, and when we're concerned about space plasmas, what we're talking about is a gas, and a gas that is so hot that the atoms have separated into electrons and ions. Basically, the electrons have been stripped off of the ions, and they do not recombine. in a space plasma typically, or the recombination rate is very slow, more accurate. Some common plasmas, the sun, right? That's the one we're going to talk about. Lightning generates a plasma in this bright flash that you see. Neon signs. Neon lights up because you're taking a gas and passing an electric current through it, stripping the electrons off, creating a plasma. And when that plasma then recombines to form neutrals, it emits light. So neon signs are a plasma, so are fluorescent lights. TIG welders and plasma cutters, it's even right there in the name. So these are plasmas you may have interacted with. In space, plasmas have very complicated motions. They not only move like a gas or a fluid, but they also respond to electromagnetic forces. So they respond to fluid motion, electromagnetic motion, and any combination of the two. So their motions can get very complicated. Another very important concept for this discussion is the idea of a magnetic field. So many of you probably have seen this kind of thing where you take a bar magnet or a fridge magnet and you sprinkle iron filings all around it, and they form this kind of bubble-looking shape. This is actually the simplest configuration of a magnetic field, and it's called a dipole. A dipole has a south pole and a north pole, and these lines, they're actually perpendicular to the lines of force, but these lines that then connect the two. And like I said, iron filings can trace out that shape. Plasmas interact very strongly with magnetic fields. In particular, these charged particles, electrons and ions, they follow magnetic field lines, and they follow them in this corkscrew kind of helical path. So wherever you have a magnetic field, I have a nice picture down here. I assume you can all see my cursor. I'll use that like my pointer. Whenever you have a magnetic field line, a charged particle will rotate about it and move along it, sort of like a bead on a string, but with a helical twist to it. And so very large magnetic fields, the same way these iron filings trace out the shape of the magnetic field around a bar magnet, the sun and the earth have giant magnetic fields, and plasmas are what trace out those field lines. So whenever you have a magnetic field in the plasma, you can imagine the plasma running right along it. Okay, so there's some terminology: plasmas, magnetic fields. Now we're going to get into a bit of history. And looking this up, this was actually really fascinating. We have some really good Colorado connections to all of this. So I'm going to start way back in 1859. And in 1859, that's basically the middle of the Colorado gold rush. So in 1858, less than a kilogram of gold shows up in Englewood. And by 2 years later, 100,000 gold seekers had moved into Colorado. That's a rush. And along the way, the city of Denver is founded, 1858. 1859, the Boulder City Town Company is organized. So the creation of these cities is a consequence of the Colorado gold rush in large part. And this is from an edition of the Rocky Mountain News. Many of you who are longtime residents of Boulder will recognize the Rocky Mountain News. Though it doesn't exist anymore, it only went out of business, less than 10 years ago. And this isn't the first edition, but it's like the 6th edition. This was the first year it was published, was 1859. So 1859, that's right in the middle of the gold rush. That's right as all these towns are being founded on the Front Range. And this is something else that happened in Colorado, reported by the Rocky Mountain News. And I'm going to read this one to you because I think it's kind of dramatic. On the night of September 1st, we were high up on the Rocky Mountains, sleeping in the open air, and a little after midnight, we were awakened by the auroral light, so bright that one could easily read common print. Some of the party insisted it was daylight and began the preparation for breakfast. Now, down here I have a picture of the Aurora, and this is something you imagine is happening very far north, right? Maybe way up in Canada, maybe Iceland, maybe Sweden. Oh, that's where they see the Aurora. In 1859, on September 1st, the Aurora came down to Colorado. And not only did it come down to Colorado, but it was so bright in the sky, they thought it was daytime. Now I'll leave you to think about that for a moment as I talk about this next section. What was going on at that time has since been termed the Carrington Event. And the reason it's called the Carrington Event is because of an amateur astronomer, Richard Carrington, and you know, amateur, take that lightly, he had a private observatory in his country estate, so amateur. He observed what we now call a white light flare from a group of sunspots. Basically, he's looking in visible light and he sees a flash from a group of sunspots. What we now know is that when that kind of flare happens, that signals a tremendous energy release on the surface of the sun. 3 days later, Earth's magnetic field starts to change, and it changes very rapidly. And what ends up happening is a structure from the near surface of the sun has erupted, traveled out through the solar system, and slammed into Earth's magnetic field. And this is what we call a geoaffective, meaning it impacts the Earth system, solar storm. And this Carrington event, the one that happened in September 1859, was the largest one ever recorded. Now, granted, we haven't been recording them for that long, but I'll tell you in a second why this is particularly important. So on Earth, what do we see? We see Aurora as bright as day in the Rocky Mountains. It literally turned night to day. The Aurora, something you usually think of as showing up in Iceland or Sweden, is in Panama and the Caribbean islands. This means that the entire atmosphere of the Earth is being lit up all at once. And telegraphs, which in 1859, the only long conductors that existed, were telegraph wires. And what happened to these telegraph wires, some of them just failed outright, some of them burst into flame, and some continued to operate even after the operators had removed the batteries because there was so much current flowing through these long wires. And what Carrington determined, he put these two together. He said, I saw a white light flash. I realized that all these responses happened on Earth. The two are connected, and that's why it's named after him. What he determined was that solar activity can produce magnetic activity on Earth. And what he was trying to understand is what carries that solar influence to Earth. You know, even since 1676, people had a pretty good idea of the speed of light, and they knew that whatever left the sun when Carrington saw that big flash and arrived at Earth 3 days later had to be much, much slower than light. And so the idea is maybe there's a wind coming off the sun. Solar wind, very evocative. And I have this at the bottom here. Imagine what would happen if we had a Carrington-class event strike the Earth's magnetic field today, right? So today, our long conductors are not just telegraphs. They're power lines that cover every, not every continent, but just about all the continents, at least the ones where people live. We have oil pipelines that run all over the place. We have undersea cables, all sorts of infrastructure that we rely on for our daily lives would suddenly have so much current going through it that some non-significant fraction of it would just burst into flame. And that's an impressive thing to think about. Okay, so where do we go from there? There were other hints at the time that there was such a thing as a solar wind. In particular, I point out a couple of people. One is George Hale, who demonstrated that sunspots are magnetic. And so now we know the sun has a magnetic field. It was long known that the Earth had a magnetic field. And so now we have these two magnetic fields that must be talking to each other somehow. And then in 1958, a fellow by the name of Eugene Parker takes this knowledge of solar magnetism, understands that the solar atmosphere is ionized, meaning a plasma, and introduces a magnetic field into a model that says the sun is continually ejecting a plasma. And from that model, he predicted that the solar wind would take on this kind of spiral configuration where the magnetic fields of the solar wind would get bent into this kind of lawn sprinkler type shape. Now, this was a purely theoretical paper in 1958, and Parker actually got a lot of grief from his referee when he tried to publish this. They said, there's no way that could possibly correct, and you have nothing to prove this on. Well, not long after, humanity entered space. In 1959, well, actually, this would be right around Sputnik, right? So it's actually pretty close to Sputnik. I think it says 1958 on here because that's when he finally got the paper through, but he submitted it quite a long time before that and had a long battle with the referee. In 1959, the Soviet Union launches a spacecraft called Luna 1. And this reaches an altitude of like 100,000 kilometers. They were shooting for the moon. They didn't make it. But what happened basically was that the Soviet Union launches Sputnik. And Sputnik is such a big world-changing event that humanity has now reached space. And of course, Stalin, being a dictator in charge of the Soviet Union at the time, says, you must launch something else. You must do something else incredibly dramatic, to honor some sort of political anniversary or another. And so the scientists scramble and they say, oh gosh, what are we going to do? Why don't we just take something that looks almost exactly like Sputnik and just shoot it higher? And that's what they did. So on this Luna 1 spacecraft, they had what's called a scintillation counter, they had a Geiger counter, and they had a magnetometer. These are instruments that were capable of detecting the solar wind. And in fact, they did measure the solar wind. But at the time, there was no ability to record data on a spacecraft. Spacecraft had to continually send their data back to Earth all the time. And you just got, what was broadcast in that real time. And when Luna 1 was in the solar wind, it just so happened that orbit of the spacecraft and the orbit of the planet were such, Australia received all the data. So Australia has all this data that's encrypted with these Soviet codes, and they're not going to share it with the Soviets. They have no idea what's in this information, and the Soviets are not going to share their ciphers. And so no one shares, and no one learns that this spacecraft actually reached the solar wind. Several years later, the United States launches Mariner 2, and this is a mission to Venus. And so this has to get well beyond Earth's magnetic field, and it contains an instrument called the solar plasma spectrometer. And Marcia Neugebauer in 1966 publishes the very first direct observation demonstrating that there is in fact a solar wind, that the sun's atmosphere is continually blowing off into space and affecting all the planets. And so that, let's fast forward 60 years to where we are now. This is a picture from 2017, but it's still mostly accurate. And now we have this fleet of spacecraft, both that spend their time within Earth's magnetic field, and some that have gone well beyond Earth's magnetic field. We have spacecraft that specifically study the sun continually, like IRIS and STO and RESI. And so we know a lot more about the sun and the solar wind than we did back then. And I'm going to play this. This is a video from the Solar Dynamics Observatory. Basically, it's a series of images that have been stitched together. And this is our current view of the sun. So the sun is not some featureless dot up there in the heavens. The sun is a very dynamic body. You can see that eruption that just happened down here. It has these very complicated magnetic field structures that thread through the surface and extend up and out through the entire solar system. And on those threads of magnetic field run that superheated plasma from the solar surface. Anyway, this is just a pretty picture. I can sit and watch these things for days. But where I want to get to next is I want to describe how we see the solar wind. We now have not only measurements from spacecraft that can capture the solar wind, but we have literal photographs of the solar wind. So what happens here is this is a very, very sensitive camera designed to measure scattered light. And it measures light scattered by density fluctuations in the solar wind. This picture is from a spacecraft called Stereo A. And so the picture down here, this is where Earth is in its orbit about the sun. Stereo A runs a little bit ahead of Earth. And so Stereo A in this picture is looking back this way, such that the sun is on the right and the Earth is off on the left and Venus is somewhere in between. So I'm going to play this video for you. And this is a stitching together of several cameras on stereo done by one Craig DeForest, who works at Southwest Research here in Boulder. And what you're going to see is from the surface of the sun on out, you can watch the fluctuations of the plasma density. This is literally what we call the solar wind. And you can watch it now stream away from the sun. So this continual stream that was hypothesized way back when by Parker, speculated on even as far back as Carrington and before, and then measured by Marcia back in 1960s, is now directly observed in this way by stereo. And you see that structure that just came off. I'll play it one more time. You'll see it'll start up here. Ready? Come on, where is it? Where is it? There's a big release. There it goes. That thing is what's known as a coronal mass ejection. So that's a big piece of the solar atmosphere that is blasted out into space and then encounters Earth's magnetic field. That's one of the structures that ended up causing the Carrington event, a much bigger one than the one observed here, but still the same. And so now we understand that the sun's gravity and energy define a space that we refer to as the heliosphere. This is the bubble in which our sun controls the motions of plasmas and the magnetic fields before you reach interstellar space. So everything that we define as the solar system is influenced by the sun's magnetic field, and it's defined by the solar wind. So this bubble that we live in, that's separate from the rest of the galaxy, is defined by the solar wind. And finally, the very last thing I want to say in this section is that the exploration of the solar system, and in particular the solar wind, is an incredibly new science. Remember when I was going back through the history, and the very first person to make a correct theoretical prediction for the solar wind was Eugene Parker? Well, there's Eugene Parker attending a solar probe meeting, a solar probe planning meeting in 2010. He's 83. I'm in the back here smiling like a goof. But this shows you how young of a science this is. I mean, this was the first person to make a correct prediction about how the solar wind should behave, and he's still around. And so this is very, very new stuff in the terms of history of humanity and how we understand our place in the universe. Okay, so that brings Act 1 to a close, and we'll try out and see how this Q&A thing goes.
And yeah, David, we've had a couple of questions come in. Someone just added that it does look like the listing that you'll have in your feed of participants is alphabetical. So if there is someone you want to call on for a raised hand or because of a question that they posed, Emily should be able to find them and unmute their mic.
Excellent. Okay, so I will start by trying to answer one or two of these common questions, and then we'll ask for hands and see if we can answer one or two extemporaneous questions, and then we'll move on to the next act. Okay, someone brought up that Stalin died in 1953. I'm actually not sure about that. That may be true. I'm not a political historian, so I may have made an error there. I apologize. Okay, so whoever was in charge of the Soviet Union at that time absolutely did demand that something else be launched to follow on to Sputnik. Of that, I'm positive. So minor correction. Question, is the solar wind the same as solar flares? Absolutely not. Those are two completely different things. So the solar wind is a continual flow of particles off the solar atmosphere out into the solar system. Solar flares are impulsive events. So they're sort of very, very rapid compared to the continual flow of the solar wind. So you can imagine the solar wind flow is this always omnipresent kind of thing that all stars do, which is bleed off the outer part of their atmosphere. And then solar flares are these little impulsive events that happen occasionally. And I'm going to address this too. Someone brought it up as anonymous, but I think it's very important to describe, especially at this moment in history. Someone says there's not one woman in that group photo. So I'm going to bring that back up. There is not. No, there is not. And that, I think, is a consequence of, well, it's a consequence of a lot of things, right? And it's a bit of a sad commentary, I think, on how the STEM fields exist today. And I think it's something very important to change. What I would say is now, 10 years later, when you take this same picture and you look at the people who are working on the solar probe team, there are many more women in the picture now. And in fact, they're making incredible contributions to solar probe and really making it happen. And like I said, you know, back even in 1962, the very first observation of the solar wind was done by a female scientist. So there's a rich tradition in here. This photo does not, I think, reflect where we are now. And so all we can do, I think, is improve on where we are now. Okay, I'm willing to take one or two questions if folks want to raise hands. Please use the Okay, we have a question from Sharon. Can she be unmuted to speak?
I just unmuted her.
Perfect. She seems to still be muted.
You might have to accept that you are unmuted, Sharon. I just allowed you to speak.
Did you hear me?
Now we can hear you. Please go ahead with your question.
All right. What causes the solar wind and why does it go out? Why doesn't it just stay right there around the sun?
That's an absolutely amazing question, and that is the question that motivated Solar Probe to exist in the first place. There's some basic ideas about how the solar corona, the very outer atmosphere of the sun, is incredibly hot. And it is so incredibly hot that the thermal energy of the particles there can overcome gravity and escape from the sun. So that's our sort of general understanding, but the very specific understanding of why the corona is as hot as it is and why that leads to the corona becoming the solar wind, that's why one of the main reasons why Solar Probe was imagined and created in the first place is because we really don't understand that yet. And that's an excellent question. Thank you. Okay, I'm going to press on in the interest of time. And when we come to the end of the next act, please feel free to raise your hands. I think having some interaction is really excellent. So part 2, right? We're going to talk about solar wind science. So despite all of these observations, right, 60 years of spacecraft going up there, directly measuring the solar wind, directly observing the sun, we have fundamental questions about the solar wind that are unanswered. And yeah, so I put up a Calvin and Hobbes comic, right, because I'm at an age where I was a kid when the Calvin and Hobbes books were coming out. And I just love this one, right? Curiosity is the essence of the scientific mind. Well, I'm going to see what happens when I inhale milk into my nose and laugh, right? So basically, we want to find out what's out there, right? This is exploration. So these unanswered questions, this one, actually that Sharon brought up, is what heats and accelerates the solar wind? Why is the solar wind able to escape the solar gravity? This is a fundamental question that we do not have a definitive answer for. We do know that the solar wind accelerates to supersonic speeds very close off the surface of the sun, within a few solar radii. And that's something that Parker predicted back in 1958. He predicted that it must be so, but he didn't have a reason what would be causing it. So he sort of had the why, but not the how. In fact, there are multiple types of solar wind. There's what's known as fast solar wind and slow solar wind, and they're different in speed by a factor of 2 to 3. Why does that happen? We know that the solar wind is self-heats. It actually gets hotter as it propagates away from the sun. Not in a global sense, but it gets hotter than an expanding gas should be, just from, if you took a fixed temperature gas and you allowed it to expand, we have a pretty good idea based on our knowledge of thermodynamics what that should look like. And the solar wind doesn't do that. So that kind of expansion is what's called adiabatic expansion. That's this blue line on this curve. This is showing you distance away from the sun in terms of AU, which is the distance between the sun and the Earth. So a factor of 1 on here means all the way to the Earth. And this T is the temperature, in particular the temperature of the protons. And so the prediction is this blue line, and what we see is the red line. So in fact, what we're seeing is that the solar wind is hotter than it ought to be, and it continues to heat as it moves away from the sun. How is that possible? All of the observations we've made so far have been relatively near to the Earth. One spacecraft called Helios got very close into 0.3 AU, but that's still not close enough to answer these questions. So what we need to do is we need to measure the solar wind near its source. Another major question, what structures in the solar corona? You saw that beautiful video of the sun rotating and all this magnetic structure near the surface. What structures are the sources of the solar wind? There's some evidence. This is a sequence of images where you can see this thing called a helmet streamer. And you can see it start to form in time, and then it kind of turns into this bubble, and then it erupts. And so there's this idea that perhaps there are specific structures on the sun that correspond to the solar wind. Maybe some of these correspond to the fast wind, maybe some of these correspond to the slow wind. This is an open question. And it's open because we need to get closer to the source, we need to get closer to the sun to be able to answer it. A third major question is that from the sun, we know that occasionally there are these blasts of incredibly energetic particles, things that are moving very close to the speed of light. So these are called SEPs, or solar energetic particle events. They're associated with solar flares sometimes. They're associated with some small fraction of coronal mass ejections, which again is a piece of the solar atmosphere launched out into space. Some of them happen gradually, some of them happen impulsively. Why? And in particular, the transport between their source and when we observe them, we don't know how or to what degree the transport processes smear out the source. And SEPs can be very dangerous to astronauts. These are things that can give astronauts fatal radiation doses within hours. These can destroy spacecraft electronics, and they heavily degrade solar panels. So being able to predict them and not only predict them, but understand their properties once they start, I think is going to be vital to human exploration of the solar system. And I have this neat video. This video was taken from a spacecraft called SOHO. This is one that observes the sun with multiple cameras. You can see the images of the cameras nested on one another here. And when I play this, what you're going to see is first a blast of plasma out from the sun, and then you're going to see the screen speckle with little white dots like snow. All those little things that look like streaks, what you're watching are those solar energetic particles striking the detector. And when they strike the detector, they saturate individual pixels, and you get these little white streaks. Now, oddly enough, astronauts on the International Space Station have known to, or have reported that they occasionally see streaks in their vision. And it turns out what's happening is when solar energetic particle events happen, because the astronauts do not have the Earth's atmosphere to protect them, as those solar energetic particles penetrate right through the human eye, you get what's known as Cherenkov radiation. Basically, the speed of the object has to change a little bit as it's passing through your eye, the fluid in your eye, and it gives off a light. And so exactly what this detector is seeing, this sort of rain of snowflakes, that's very similar to what your eye would pick up if you were being hit with one of these solar energetic particle events. So we really don't know how these things are created. We really can't predict them very well. And so what we need to do is to get closer. And with that, I'm going to end Act 2 and then open it up a little bit for some of the questions. If there's anything anyone would like to discuss. Okay, it seems we don't have any chat-related questions for the moment. Would anyone like to use the raise hand feature and ask anything? Kamiko? Please go ahead.
Can you explain about the magnetic fields on the sun?
What aspect of it?
Well, it looked to me, like for instance, on Earth, you have more or less distinct north-south poles for the entire planet.
Right.
And does the sun have the same structure, or is it kind of in localized areas?
Yeah, very good question. So to first order, like you said, the Earth's magnetic field is more or less a dipole when you're close to the planet. When you're far away from the planet, it's not. It actually gets stretched into a shape like a comet by the pressure of the solar wind. But very close to the planet, it does look like a dipole. The sun's magnetic field goes through these cycles. So every 11 years or so, it goes from what's called solar minimum to solar maximum. When the sun is at solar minimum, which it is right now actually, then it has a very dipole-like shape to it. And there's kind of a cartoon right here where you get something that's more or less a dipole. You have the magnetic, you have a magnetic north and a magnetic south, and they're very clearly defined. But at the other end of the solar cycle, what's called solar maximum, the sun looks like this. And what ends up happening is you get all these so-called active regions, or these places where the solar magnetic field starts to kind of pop out dramatically. Those are the boundaries between positive and negative magnetic field lines. And so the positive and negative magnetic fields in this nice clean dipole, that goes away. The sun basically mixes up all of its magnetic field, and then 11 years later, it comes back and it's calm again. And so there's this so-called solar cycle where the sun goes through a dipole to non-dipole, back to dipole type configuration. So that was a really good question. Thank you. Okay, if there's no further questions, I will go on to the next piece. So this part is about preparing a mission. So science-wise, we know a solar wind exists. We've measured it for about 60 years, roughly, from the near-Earth environment, and we have a pretty good idea about how it behaves near Earth. We have a few probes that have gotten closer, but they haven't been able to answer these very fundamental questions because they simply have not gotten close enough to the sun. So this is a little bit of history of Solar Probe itself. So in 1958, Eugene Parker's paper on a supersonic solar wind is published. And in 1958, so-called Simpson Committee recommends a solar probe to Congress. Well, we know how that went, right? And in 1958, the other big event was that NASA was founded. So in fact, solar probe has been an idea for longer than NASA has existed. And in 1962, this became a different concept. They said, well, maybe we'll make it a solar observatory. Maybe it will orbit the sun. And then nothing happens for 10 years. And in 1974, at the time, what was West Germany, leads a mission called Helios. Now this mission, they launched 2 spacecraft, Helios 1 and 2. It's over here, kind of non-coincidentally, looks like a disco ball, kind of folded out a little bit. Maybe that had something to do with the era, but I think it had more to do with keeping the spacecraft cool. So the Helios launches and it reaches 65 solar radii. I'll give you, in a moment, I'll explain how close to the sun that really is compared to how close Solar Probe gets. And these, are led by a European nation. And so NASA says, oh, maybe we better get back to this Solar Probe idea. The Europeans have practically beat us to it. So in 1978, they fund a solar probe concept study. And they say, okay, let's put together the idea of a solar probe. What do we need? They come up with this concept study report that says, here's exactly what we need. And then nothing happens for 12 years. In 12 years, about 1990, so a little bit later, NASA proposes another concept and they say, well, let's do something called solar orbiter. Yeah, let's do solar orbiters. So they all get together. Many scientists gather together, say, here's what we need to measure. Engineers get together, say, here's how we're going to do it. No funding materializes. And so this sits on a shelf for another 10 years. In 2003, the National Research Council designates Solar Probe as something that needs to happen, quote, as soon as possible. In 2003, the brand new NASA Chief Administrator says, nope, and redlines out any funding for Solar Probe, saying this will never happen. But in 2005, after another change of NASA Chief Administrator, Solar Probe is now labeled the highest priority for new resources. In 2008, Solar Probe Mission Engineering Study Report is put together, and they rename it. Instead of calling it an orbiter or an orbiting observatory or just Solar Probe, now it's Solar Probe Plus. And in 2010, proposals go out and are accepted for Solar Probe Plus instruments. Basically, what do we want to measure? What experiments do we want the spacecraft to carry? And in 2010, that's when engineering begins in earnest, and we all start actually building this thing. In 2017, the spacecraft and instruments are completed. In 2018, it's renamed Parker Solar Probe in honor of Eugene Parker, having predicted way back in 1958, before anyone even observed it, what the solar wind ought to look like, its basic properties and magnetic characteristics. And in fact, this is significant for a lot of reasons, one of which is this is the very first NASA mission ever to be named after a living scientist. That had never been done before. And then in 2018, we completed our first pass near the sun. And of course, 2020, it's now. Here's an image, a long duration exposure from the solar probe launch down in the Cape. I was lucky enough to be able to go and see that. So for all this time, from about 1978 up until 2008, the concept of solar probe looked like this, which of course is very different from what we ended up. And the idea here was that to launch from Earth and to get very close to the sun, to get within 3 or 4 solar radii, the only way to do that using conventional rockets or chemical rockets is to launch from Earth and get out to Jupiter. So very counterintuitively, you actually have to go out in the solar system to be able to get close to the sun. And that just has to do with how much angular momentum the Earth has going about the sun. The only way to slow yourself down enough to fall into the sun is by using Jupiter. And so the original mission concept was to fly all the way out to Jupiter, slow yourself down to almost zero in the frame of the sun, and then allow gravity to drag you all the way back in. This was an extremely challenging idea because it not only had to survive the extreme heat near the sun, but it had to survive the extreme cold all the way out at Jupiter. And it had to be nuclear powered because there weren't solar panels at the time that could be large enough to power it both out here and in here. So the engineering was just very, very challenging. The idea of a Solar Probe Plus concept came along in about 2008, 2009, maybe even a little before that, but it was published here. And the idea here is that instead of going out to Jupiter, what we're going to do is we're going to give up a little. So instead of trying to get all the way into 3 or 4 solar radii, we can get into about 9.5. And if we get into 9.5, we can answer the vast majority of science questions that we have with a mission that is feasible in an engineering sense. And so this mission involved orbits of the sun and then encounters with Venus. So the spacecraft actually comes very close to Venus to slow itself down in the frame of the sun and allow it to fall in ever so closely. Now here is showing you how close Solar Probe is going to get to the sun. And in fact, this is to scale. Not the planets, of course, but the line here. You always see those drawings that say not to scale. Well, this one is to scale. This is the sun, and the radius of the sun is 1. Right? That's the surface of the sun. That's the so-called photosphere. So that's a distance of 1 in this plot. All the way out here at 215, that's where Earth sits. So that's the orbit of Earth, is at 215 solar radii. Venus is in at 155, Mercury in at 83, and the Helios spacecraft launched in the 70s by West Germany made it into 65. That's as close as they could reasonably go with the technology at the time. Solar Probe is going here, all the way into 9.8 solar radii. Much, much, much closer than Mercury, much, much closer than Helios, and really not that far off the surface of the sun, the so-called photosphere. This mission is broken down into 24 orbits that will take place between 2018 and 2025. And every couple of orbits, we step a little bit closer to the sun. So the very first few orbits went out to, let's see, how do we read this? Oh, they have it in units that are not very useful. Okay. The very first few orbits went out to 36 solar radii, so that's as close as the spacecraft got. That's down here. So the blue curve is showing you the distance. So the first couple were out to 36 solar radii, and then we stepped in a little bit to 26, which is where we are now. And the next orbit will bring us into 20, and we'll continue to step closer and closer and closer. Right, we are here. So the mission currently is inbound onto orbit 6, so we're kind of on this curve somewhere like that. There are many dangers. There are many things that can destroy Solar Probe. The most obvious one is probably the temperature, right? You get very close to the sun and things get very hot. In fact, the heat shield, which I'll show you in a minute, I'll show you what that feature is on the spacecraft. The heat shield and the electric field antennas, which are part of the fields instrument that I worked on, they're going to get up to 1500 degrees C, roughly 2600 degrees Fahrenheit. So they hit these incredible temperatures. These are temperatures well above most things, where most things melt. And in fact, if the spacecraft has any sort of pointing error that's greater than 2 degrees, if it points off of the spacecraft sun line by just more than 2 degrees, it will melt. Not only will it melt, but it will melt, and then it will turn into a gas, and then that gas will turn into a plasma, and it will become part of the solar wind, which is a little poetic, but there it is. Not only that, though, but when you get far away from the sun, out almost to the orbit of Venus, the heat shield, the thing that keeps you safe when you're close to the sun, is now keeping you too cold. And now you're so cold that your instruments might freeze and die. And so what you need instead is heaters that have to run. Several of the instruments, including the antennas and what I'll describe later is called a Faraday cup, which is something that directly measures the solar wind ions, those have to be in full sunlight to operate. And so we had to design instruments that could stare at the sun at 2,600 degrees Fahrenheit and still function. The spacecraft, of course, has to survive radiation, these solar energetic particle events that I mentioned. You know, when you get closer to the source, it's sort of like standing closer and closer to the nozzle of the fire hose. The flux is going to be much higher. You're going to get hit with a lot more of these if one of these events strikes your spacecraft. Another thing that you often don't think about, but turns out to be pretty deadly to a spacecraft, is a dust impact. The solar system is full of so-called interplanetary dust, basically nearly microscopic or millimeter type dust grains left over from asteroids smashing into each other and grinding into little bits. And the spacecraft will eventually be moving 180 kilometers per second, which is an incredibly fast speed. And in fact, it will literally be the fastest human-made object. It's already achieved that by traveling at 90 kilometers per second, outdoing the New Horizons spacecraft that hit, I think, something like 64 or 65 kilometers per second on its way out to Pluto. Solar Probe has already beat that, and eventually it will be going twice as fast as it is now. And when you're moving that fast and you run into a grain of sand, that grain of sand is going to punch through the spacecraft like it wasn't even there. And so those impacts can damage, for example, the cooling system that keeps the heat shield operational. It can puncture the solar arrays. It can destroy pretty much anything it touches. A sort of advantage that we have are these are very rare. And then another sort of danger that we have to survive is the solar arrays. You wouldn't imagine this, but when you get close to the sun, you're actually starved for power. And what goes on here is that the solar panels can only get so hot. And so you have to reduce the area that's exposed to the sun in order to keep them cool enough to operate when you get close to the sun. And so you have to fold them back and away. And they do this feathering behavior where they fold toward and away the spacecraft on every orbit. And it has to survive all of this stuff for 6 years. So here is what the spacecraft looks like. This is the engineering solution that's designed to survive all this incredibly hostile environment and provide the science measurements that we really need and want to be able to answer our questions about the solar wind. The main feature is this heat shield, this big carbon-carbon thing on the front that tries to block the sunlight, basically, and the rest of the spacecraft, for the most part, hides in the shadow. These big features here are radiators. And so there are literally tubes filled with literally water that pass back and forth between the heat shield and the radiators and allow a heat exchange between the hot heat shield and the radiator to allow the radiator to dump that energy out to space. So this thing is literally water cooled. Let's see, this is the spacecraft bus in the back that carries all the electronics and the instruments and the communications. This is the high gain antenna that allows it to talk back to Earth. And these are the solar panels, and you can see how they're on these little motorized structures here that allow them to feather back and forth. So they kind of hug the side of the spacecraft, and then they deploy more fully like this. And the spacecraft has this sort of tail out here, which is this boom. That boom holds some instruments that are very, very sensitive and need to be held away from the noisy electronics of the spacecraft. So I work on the fields instrument. The fields instrument sensors are here, these antennas that measure electric fields. This is basically a giant voltmeter. And fields also includes these magnetometers, which measure magnetic fields. There's two back here, and there's one at the very tip. There's another and small antenna back here. particles, so the solar wind directly, are measured by the Faraday cup, which is this guy here, as well as these sensors back here, the so-called sweep span sensors. They also measure the solar wind. One measures electrons, the other measures ions. This one is called ESIS. This is an instrument that measures very high energy particles, in particular the solar energetic particles that I was describing before. Here's WHISPER. This thing takes pictures of the solar wind, again, those density fluctuations that you can see. So everything's mounted back here, hiding in the shadow from the sunlight, except our antennas in the Faraday cup, which have to be deployed. The WHISPER imager is a telescope, very, very sensitive telescope that looks off to the side. It does not look at the sun, it looks 90 degrees to the sun. And you can see that here, it's hiding in the shadow. It has no line of sight to the sun because it would melt, but it can look off this way. And it takes these beautiful images in which you can see structures like this, which is a solar streamer. So it's a magnetic field that carries sort of extra plasma off the sun. And this kind of lumpy structure you see up through the middle of here is what the galaxy looks like in this wavelength and this kind of camera. This is provided by the Naval Research Lab. The ESIS instrument is provided by Southwest Research. This looks like so. It has this funny mushroom-shaped structure on top and a couple of high-energy particle telescopes. The low-energy solar wind, ions, and electrons are measured by the SWEEP instruments provided by the Smithsonian Astrophysical Observatory and UC Berkeley. This is the Faraday cup. These are the sensors that measure sort of off to the side, whereas the Faraday cup stares at the sun. And then near and dear to my heart is the fields instrument. This measures electric and magnetic fields, and it's a collaboration between UC Berkeley, University of Minnesota, Goddard Space Flight Center, LASP here at University of Colorado, and LPC2E, which is a French institute that provided the search coil. We have a considerable amount of electronics, which again are things that are near and dear to my heart. This is what the search coil, this is a magnetic field sensor for high frequency or very quickly fluctuating magnetic fields. And this is a sensor for low frequency magnetic fields called a flux gate. And this is our pride and joy. This is the thing we built at the University of Colorado. It's an electronics board. The way I like to think about these things is this is artisan electronics. Only one of these things will ever be built. It is completely custom. And only one of these things ever needs to be built, right? And for the Solar Probe mission. And I call out here the folks at LASP who really made this happen. You may know some of them. There are many others, many more than I could list here, but I wanted to put up the main players. So this piece of electronics, even though it seems like such a small thing, there are 2,200 individual components on here, the vast majority of which, well, not the vast majority of it, many of which were hand soldered onto this board. This thing uses 2 watts. 2 watts, which is absolutely incredible considering the amount of components and signal processing this thing does. It weighs less than half a kilogram, so it's about a pound. It fits in a very small space. It can take a huge radiation dose, operate over a huge temperature range, and it's supposed to operate without fail continuously for at least 6 years. It will probably last quite a bit longer. The other thing I want to share with you is a couple of these wonderful pictures from when Solar Probe was sort of being born. These are taken at the Applied Physics Laboratory in Johns Hopkins over on the East Coast. And this is the Solar Probe spacecraft as they were putting it together. This is the Solar Probe spacecraft inside what's called the thermal vacuum chamber. This is a place where you suck all the air out and you sort of make an environment that's sort of similar to space. So they were trying to mimic some of the space environment during testing. And this is the Solar Probe spacecraft being assembled. You can see the radiators, the heat shield has not been added yet. You can see this sort of cabinet door piece of the side open and all the electronics boxes being hooked up inside. And then take a look at this on the right. So what's happening in this image is that this spacecraft, this thing which has taken nearly 10 years to build, which has taken nearly 50 years to conceive of, is hanging by a couple of straps from the ceiling. And not only is it hanging from the ceiling, but here's this guy pulling it back like a pendulum, and he is literally about to let it go and let it swing This is what's called a magnetic swing test. It is fairly scary in the sense that you don't want to drop this thing, but it's incredibly necessary for calibrating the magnetic field signatures that the spacecraft makes, so we can separate the real data from the noise that the spacecraft is making. So this is what's called a magnetic swing test, and it's a very dramatic moment in the testing. Okay, so I've walked through an awful lot there. I went from the history of, the first idea that we might even want a solar probe, all the way up through the instruments and the orbit and the spacecraft. And here we are at the cusp of launching. And so before we launch, I would like to ask if there are any questions that I can address. Let's see. Okay, I see a number of them here in the chat window. Let's see. Okay, so here's a question I can answer right away. What specific function does the board built by CU perform? So this electronics board that I pointed to here is what's known as a signal processing board. So what it does is it takes in signals from these antennas. So these are voltage sensors. It takes in signals from there, and it takes in signals from this magnetometer. And what it does is it crunches on them. So it takes these raw analog signals and it turns them, first it digitizes them. Well, first it filters them, then it digitizes them. And once they're digitized, it performs some pretty complex signal processing to take the enormous amount of data being collected and to reduce it into a small enough package that it can be sent back to Earth efficiently. Keep in mind the transmitter on the spacecraft operates with something like 100 watts. So this is sort of like shining a light bulb, halfway across the solar system, or at least between the sun and the Earth. So halfway the distance between the sun and the Earth, you shine one light bulb and it puts out radio emission, and you try to pick that up from Earth. So it's very difficult to send data back. And one way we get around that is by heavily compressing and processing the data before we return it to the ground. And so that's the main function of the board from the University of Colorado. And in doing so, you have to be very cognizant of what science you want back. Because in terms of compression, you want to reduce the data volume, but you do not want to throw away any of the valuable science knowledge that you might get. And so this is where scientists like myself come in, is trying to design these signal processing algorithms to compress the data, but not throw out the pieces that you really care about. So there was another question on here. How do we know that the ions, for example, in a solar energetic particle event, move at a speed close to that of light? So these instruments here, the LET, which is a low energy telescope, HET, which is a high energy telescope, these typically have very thin wafers of semiconductor type material. And what they observe is when an energetic particle strikes that layer after layer of wafers, it penetrates through a certain number of them. And the number of layers it penetrates through is related to the energy of that particle. And so by measuring the number of layers that it penetrates, we measure the energy of that particle, and we use that energy to understand how fast the particle was going when it first hit. And so that's one way in which we can directly measure the speed of these energetic particles and know that they are moving very close to the speed of light. So at this point, I'm willing to take a question or two if anybody would like to raise their hand and ask something. Okay, and if not, I will move on to Act 4. So here we've explained why we care about the solar wind. We've explained why a solar probe has been sought after for so long. We explained how we built up a solar probe. Now we're going to launch it. And so I have for you a launch video that I'm going to share. If I can make my screen the right size. Okay. So I'm going to stop this document and I'm going to open this one. Hopefully you all can see that. It's a YouTube video. I've included the link so that if and when these slides get posted, you all can check it out. We're going to watch a little bit of the Parker Solar Probe launch.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
Seconds into flight. Chamber pressures continue to look good on all 3 boosters. Now 35 seconds in. Chamber pressure on the core booster is throttling down to the partial thrust mode. Response looks good. Now 50 seconds into flight. Strap-on boosters look good in the full thrust mode. Core booster looks good in the partial thrust mode. Now 1 minute into flight. Vehicle trajectory looking good right down the middle of the range track.
And so, to spoil it for you, the launch went beautifully. The spacecraft went into exactly the orbit it had to go into in order to start its journey to the Sun. This here is an image that I took on my cell phone when we got to visit the launch site a little bit before the launch. This was a very cool thing to watch. If you ever get the opportunity, I highly, highly recommend you watch a rocket launch. There's places you can get to that are only a few miles away from the launch site, and it's just an incredible thing to see. So I highly recommend it, should you get the opportunity. So here is our long-awaited data. So what we have on here is what the spacecraft observed, at least in one of the measurements, on the first so-called perihelion. That means a close approach to the Sun. And this is something that was published in Nature not so long ago. And so what you're seeing on here is this so-called B. B is the symbol used to indicate the magnetic field, and B sub R means it indicates the radial magnetic field. So the portion of the magnetic field of the Sun that points either toward or away from the Sun. And this is what we saw. So you can see the black is the real data. You can see it jumping up and down with these kind of spike-like forms. It gets bigger and bigger and bigger as you get closer to the Sun. And then as the spacecraft recedes from the Sun, you can see it gets smaller and smaller again. Now, what was expected? What we thought we were going to see, based on years and years of observations and modeling, is this dashed red curve. We expected the magnetic field to hug this dashed red curve, and that would be that. And that is not at all what we observed. In fact, you can see that it kind of vaguely follows that dashed curve occasionally, but what you see are these jumps, these spikes, where the magnetic field very suddenly and violently reverses direction. This is a structure that we've since started referring to as a switchback. Basically, the magnetic field, even though it's pointed one way, it suddenly flips and then flips and then flips. And these type of structures, really, you can only see them from solar probe. You can see very weak remnants of them from further out spacecraft, but you have to get close enough to the Sun to observe these in detail, which solar probe did on its very first orbit. And so the solar wind, this thing we thought we understood really well, has a whole new structure to it that we never saw before. And the only reason we can even observe it is because now we're close enough to the Sun to see it. This is the sort of an estimation of the magnetic conductivity of the spacecraft as it passes near the surface of the Sun. And so the spacecraft orbit, if you're in the frame of the Sun, looks like these first red dots, and then into these blue dots, and then kind of whipping around like that. Close approach is somewhere down here. And so on that first encounter with the Sun, we passed over this structure, a so-called coronal hole, which is a region of extra intense magnetic field near the surface of the Sun. And since then, after those first 6 months, or 6 months after the first data came back, we started to publish our results. I'm not going to get into many of these in detail, but suffice it to say right now that 4 articles ended up in Nature, 48 were published in the Astrophysical Journal, and more than 50 have been published since then. And of course, we got some great press coverage out of it. We even got the cover of Nature, which was a very cool and exciting thing to be a part of. I even put the daily camera in there for everybody here. So what did we find? What was so exciting? What did Solar Probe detect that was worth all this time and effort? First off was the thing I sort of alluded to already, which is this idea of a magnetic switchback. So the magnetic field of the sun, we sort of expected it to behave a particular way based on our observations over the last 50 years. And once you get close enough to the sun, it does not behave that way at all. It has these so-called switchbacks, or very sharp changes in the magnetic field that are a completely unexpected feature. And these switchbacks seem to be getting more intense as we get closer to the sun, which implies that our understanding of how the solar wind is born is very incomplete, and it somehow has to now account for these new structures. Another major first result was this idea of a dust-free zone. So for upwards of 100 years, it's been predicted that when you get close enough to the sun or any star, the heat from that star is so intense that it should sublimate any kind of matter that gets close enough to it. Anything like an asteroid or a comet, or these little tiny dust grains I was discussing earlier, are predicted to not exist within a certain distance of the sun. So this prediction has been made for, like I said, close to 100 years, but no one has ever been able to observe, either from Earth or from any spacecraft, this so-called dust-free zone. And so this was a major conundrum, something we know from thermodynamics should happen, but for some reason was never observed. And on the very first perihelion pass, Solar Probe got close enough to glimpse the edge of a dust-free zone. And it just so happens you have to get close enough to the sun such that there's less intervening material, and you can see that there really is this zone that's been predicted for so long. Another piece of the solar wind physics that has been very difficult to explain is that the solar wind itself is magnetically connected to the sun. And so it acts, because the sun spins, the solar wind kind of rotates with it a little bit in the frame of the sun. And so it has an angular momentum to it. It acts like a flywheel. So you're basically taking a lot of the angular, not a lot, but you're taking some fraction of the angular momentum of the star, and you're spreading it out in this great big disk away from the sun, related to the solar magnetic fields and the particles that are moving out from the sun. Well, the prediction that existed, the so-called kind of Weber-Davis behavior, is this blue line. This is what we predicted the transverse speed of the solar wind should look like. And even without that prediction, there was an idea that you really can't do more than rigid rotation, meaning that the whole solar wind would behave like a solid disk, which we know does not happen. So that's this red line. And then the other prediction, the best prediction we had, was this blue line. And look what the data are doing. They're doing absolutely nothing like either prediction. And so what this means is that the solar wind is carrying much more momentum than we think it should, angular momentum away from the star, meaning like a flywheel, it's slowing down the orbit of the rotation of the star, our sun, in a much different way than has been predicted. And so other than just being interesting physics, this applies to other stellar systems. If we try to want to understand how exoplanet stars behave, like the stars that exoplanets orbit, if we want to understand solar system formation, if we want to understand how black holes operate, we need to understand what fraction of the angular momentum of the object gets distributed through its wind or the particles around it. And as far as the sun, so far we can't explain the way the sun behaves. And if we can't explain the sun, it's going to be very difficult to explain an object much further away. And then finally, the ESIS instrument detected tiny solar energetic particle streams. Like I mentioned earlier, the sun right now is at solar minimum, meaning it's minimally active in terms of launching things off into space. And those, but what we did see is that when the ESIS instrument got really close to the sun, it observed these tiny bursts of energetic particles. And so the stuff we see from Earth turns out to be only the very largest events. When you get close, you can see that there's many, many more going off all the time. They're just much smaller. And then finally, I want to share with you this. So because I work on the plasma wave instrument, we measure plasma waves, which are oscillations of electric and magnetic fields within a plasma. And some of these that we recorded with the University of Colorado receiver are measured in the audible frequency range. So we're not measuring sound, we're measuring electric and magnetic fields, but we're measuring them at the same frequencies that our ears can pick up. And so what we've done is we've taken these electric and magnetic field signals and we've converted them into sounds that we can all hear. And so I'd like to play a few of these for you right now. And I'd like to thank Rick Wilder for putting the audio together. So what you're seeing here is a signal of a plasma wave, so an oscillating electric field that we measured with those big antennas in the plane of the heat shield. That's what's plotted here as one set of antennas, and this one's the other set of antennas. And what we've done is we went ahead and turned both into sound, and we made it a stereo sound. So one speaker will play one antenna pair, the other will play the other antenna pair. And what's down here is something called a spectrogram. So what this is showing you is time along this axis, it's showing you frequency along this axis, and then the color is showing you the power or the amplitude, the loudness of the sound. Okay, that's enough explaining. You should listen to one of these and tell me what you think it sounds like. I like that one personally. I think it sounds like standing in a windstorm, which is very appropriate, I suppose, for measurements made in the solar wind. And then there's these ones that we saw that come in these little bursts. So these are bursty plasma wave that come off as little chirps. And then a third one that we heard is what's called the so-called Langmuir wave. This was a wave that was first identified by Irving Langmuir back in 1929 when he was trying to design a better light bulb. He detected these kind of waves in a plasma, and as it turns out, solar wind is full of them. And those ones, you can hear sound much more like a whistle, like a pure tone. That's because they're so-called a narrow band wave, meaning their frequency is very close to a pure tone. Whereas these cover many frequencies as they chirp, and these ones have harmonics. So all these go off at once, which makes it sound like the blowing wind sound. Now these three types of waves that I showed you, I not only put on here because they sound very interesting, but this type of wave is something that is not observed in the solar wind anywhere, but right up close to the sun. And the closer to the sun we get, the more of this wave we see, and we think it has to do with the particles that are escaping, the ones that are overcoming solar gravity and escaping the solar corona to become the solar wind. We think those type of particles are driving these waves. So by observing these waves, we can learn more about the very edge of the solar atmosphere, which escapes to become the solar wind. And then finally, here's where we are. So we are on so-called perihelion 6, meaning the 6th orbit of the sun. The closest approach on that orbit will happen on September 27, which is coming up. And what I have on here is a graphic that shows you the location of the sun. So this is as if you, as the observer, were standing outside the solar system, above all the planets looking down. The sun is here at the center. Earth is this trajectory along here. Venus is this green trajectory along here. And then Solar Probe's orbit is the red trajectory. And this is where we are right now, literally today. And then we'll be inbound to that next close approach, which will happen on September 27th. And on that date, on that close approach, we are taking our next step closer to the sun. So we're stepping into 20 solar radii from the sun, which is another unexplored region where we've never been. And every time the spacecraft has taken one step closer to the sun, it has seen something completely new and different. And so we're very excited about just a couple of days from now, what we'll see. And so finally, I want to say that Solar Probe is part, as elaborate as I've described this mission and as many thousands of people have contributed to it over so many decades, Solar Probe is only one small part of the current era of solar and solar wind physics. Other very important pieces of this are the DKIST telescope, solar telescope, whose first light was on January 2020. This is run by the National, or at least participated in heavily by the National Solar Observatory, folks who are also here in Boulder. And then the Solar Orbiter spacecraft. Solar Orbiter stays further from the sun, but it takes more remote sensing. Basically, it has a lot more cameras on it than Solar Probe does. Solar Orbiter is launched by the European Space Agency. It went up with a flawless launch in February 2020. And so now, with these three assets combined, the most sensitive ground-based solar telescope that we've ever built, Solar Orbiter getting close to the sun and taking sort of the highest resolution space images we've been able to take because it gets so close, and then Solar Probe itself getting incredibly close to the sun. The combination of these three will tell us more about the sun and the solar wind in the next 10 years than we have learned in the last 60 years. And so with that, I really do want to thank you for your time and your attention, and I will open it up the remainder of our time for questions. Thank you. Oh, wow. Okay, so there's lots of questions in the chat. Let's see what we can find here. Is there a path in the orbit with where communication with the spacecraft is broken and data are not transmitted back to Earth? There absolutely are. So the way the spacecraft orbits, actually have a, I had a slide on this. The spacecraft orbit is arranged like so. It gets very close to the sun at one point in its orbit, and it gets very far away and kind of hangs out here for a long time as a consequence of Kepler's laws and the way gravity and angular momentum interplay. Basically, it spends a short time here and a long time here. When we're very close to the sun, the spacecraft does not communicate with Earth. We hear nothing from it when it's in here. It's just taking data. And in fact, that's a very scary thing because the spacecraft heat shield must point at the sun. Like I said, if it comes off by 2 degrees, the spacecraft vaporizes and becomes the solar wind. And so while it's doing that, we can't talk to it. It has to do it autonomously. And then when it comes back out of that close approach, we can talk to it again. We get what's so-called beacon tone, which says, I'm alive, and everybody celebrates. And then when the spacecraft gets back out to this very distant point, that's when it tries to communicate with Earth. Because first of all, that's when it's going to be, often when it's going to be closest to Earth, and it's the part of the orbit where we're not worried about taking scientific data, so we can turn on all the very noisy communication equipment. So every time the spacecraft survives one of these perihelion passes, because if you remember that whole list of dangers and things that can destroy the spacecraft, every time it comes back out, we all celebrate. So the mission is designed for 24 orbits. We've survived 5 so far. I think we're doing all right. So we have pretty good confidence that we'll survive the next couple of orbits, at least. Oh, interesting. Okay, so somebody commented that some of the audio sounds sound like a theremin or a wind, and they say, sounds like 2020. God, scary and not my favorite. So when we first produced that audio, we produced it near Halloween of 2019. And so we were hoping to release it in time for Halloween because it kind of sounded like an appropriate type sound. Didn't happen, but that's okay. Okay, there's a question on here. At high temperatures that the probe must survive due to the million-degree corona. Okay, sorry, let me try this again. Are the high temperatures that the probe must survive due to the million-degree corona or due to the light coming from the sun? Ah, that's a very perceptive question. So even though the solar corona is 1,000,000 degrees, the density of the corona is so low that there is no efficient heat transfer in the way of conduction. So like if you take your hand and you touch, a hot element on the stove, you're going to get burned, and that burn happens through conduction. Basically, the particles in the stove are moving really fast and they run into your skin. So even though the corona is 1,000,000 degrees, it is so sparse that when the particles run into the spacecraft, there's so few of them running into the spacecraft, it cannot efficiently transmit energy and heat. And so the 1,000,000 degree corona does not bother the spacecraft in the slightest. What does bother it is the solar photons. So the energy carried in the form of solar photons striking the spacecraft, that does generate a lot of heat. And so we use the spacecraft heat shield to create a shadow such that the spacecraft can hide in the shadow of all of that and keep it cool. There's a question about Venus. Does the spacecraft use Venus to get closer? It does, in fact. The spacecraft uses so-called gravity assist maneuvers. Basically, it gets really close to Venus and cheats a little, exchanging angular momentum between the spacecraft and Venus. It slows itself down a little bit and speeds up Venus a little bit and uses that to get closer and closer to the sun. And so actually, as a consequence, Solar Probe is bringing a set of instruments that have never been to Venus before. And so we're making these sort of transformative and brand new measurements near Venus as well as our main mission. And so the spacecraft operations team has been very good about allowing us to operate the instruments near Venus and be able to take these sort of brand new measurements and learn even more than we'd hoped.
So David, as we come towards the close here, maybe one more question?
Okay, so I would like to take one from someone who wants to raise a hand. Oh, we have 3 up. Nancy Cooper.
Hi, David. First, I want to thank you for this awesome presentation. I do not have access to chat for some reason, and I wondered if your PowerPoint is going to be available somehow to us.
David Means, I'll pass that to you.
Well, so I was going to reiterate for folks as we close out that there will be the recording. There were a few folks who weren't able to be with us at the beginning. The recording of this entire talk will be available on the See You on the Weekend Mission to Touch the Sun webpage, which is where folks registered for this event. If the presenter is willing to post PowerPoint slides and folks request it, we can certainly do that in the same place. So David, I think that depends on whether you're comfortable with sharing out the slide deck as well.
Yeah, absolutely, no problem. And in fact, I'd really like to do that because what I have on here is actually a good segue. Is I have a number of links that I put on here specifically for people who want to learn even more. I put on links here, for the CU APS department, the LASP over on East Campus, the Space Plasma Group, Solar Probe, Solar Orbiter, DKIST, some nice informative videos about the sun that NASA has put together, and then some History Channel and National Geographic examinations of the Carrington Event, that giant geomagnetic storm that kind of kicked this all off in the first place. So I do want to make these slides available to you all so you can follow these things and learn as much as you like about these topics. If we can we do one more question, or are we out of time?
We could do one more very quick question.
Okay, Julian, do you have a quick question?
Yeah, I was wondering, the electrical energy from plasma that's being created, is it creating a voltage that's enough to power on a device or something like that? Or what kind of electrical energy is it?
Sorry, could you try that again?
Can you hear me okay?
A little bit, yeah, I didn't get all of the question.
I was wondering if the plasma is creating a voltage enough to power on like a device or something, or to harvest kind of that type of energy.
Okay, so that's an interesting question. The plasma carries high voltage differences, that's true. There can be up to hundreds of volts per meter kind of fields in the plasma. What it does not carry a lot of is current. So you can get very high voltages, but very low current. And so if you want to operate something off of that, it's not going to work particularly well. And again, that comes back to the density of the plasma. There's so few charge carriers that your current is very low, even though your voltages are very high.
Excellent. Well, a few remarks to close out our program today. We're coming up on time. Thanks so much to you, David, Professor Malaspina, for sharing about this historic mission to the sun. We are grateful for your willingness to share your expertise and your remarkable scholarship. And thanks to everyone who participated through your many excellent questions. I'd like to also acknowledge Emily Musumeci and Sue Postma-Shears for providing technical support today. As our communications team in the Office for Outreach and Engagement, they work hard to make sure that you all hear about events like this one. You'll receive an email with a link to a short Google survey tomorrow. This is the first time we've done this type of event online in our office, and so we are really interested in your feedback. It will inform our future efforts here. And I'll just mention our next See You on the Weekend virtual lecture is October 10th. We will be crashing back down to Earth and pressing earthly concerns with a talk from political science professor Jennifer Woloch, titled Compromise in the Era of Party Polarization. And as with today's lecture, you'll need to register at the See You on the Weekend webpage. So finally, thank you all so much for attending, and we look forward to seeing you on the weekend again sometime, well, at our next presentation. Thank you all so much.